Hello all, welcome to the course Fluid Flow and Unit Operations. In this section, we will be discussing the importance of Reynolds number and the Reynolds experiment. So, to understand the Reynolds number, let us conduct a simple experiment in which we are injecting carefully injecting a dye into a flow. So, if you look at this figure, in this figure, you can see uh, there is a pipe in which a fluid is flowing at a flow rate say m1, and a dye is injected at the entrance of this pipe, and the color of the dye is say red. So when the flow rate say m1 is very low, that means at low flow rates the dye flows in a straight line along with the fluid flowing in the pipe. Now what you did in the second diagram, you increased the flow rate. Say here m2 is little bit greater than m1. You can observe that there is a blur in the dye flow after a some distance from the injection point. Now if you consider why it is happening, when you increase the flow rate, so the fluid inside the pipe is flowing both axial direction as well as radial direction. So you can see when you increase the flow rate of the fluid, the dye is moving in radial direction as well as. If you say further increases the fluid flow, that is m3 is further greater than m1, you can observe the dye is moving radially as well as axially, and the blurring in the dye is increased. So what is happening here, the from this experiment you can say when the flow rate is low, the flow is called as laminar flow. When the flow is intermediate, this in the second figure, as in second figure, the flow is called transition flow. And when you further increase the flow rate, you can see that dye is completely blurred in the flow. So that type of flow is called as turbulent flow. So to characterize this flow, Reynolds conducted this experiment in 1874, and this experiment is called as Reynolds experiment. And while conducting this experiment, Reynolds observed that the flow behavior is influenced by two types of forces. One is inertia forces and another one is viscous forces. So if you look at the inertia forces are the forces which are responsible for the flow of the fluid, whereas viscous forces which reduces the flow, that means flow rate, like your viscosity and the friction between the surface of the pipe and the fluid flow. So after conducting this experiments, Reynolds concluded that the inertia forces are a function of the density of the liquid and the diameter of the tube in which the liquid is flowing, and the average fluid velocity, here it is indicated as u bar. And the viscous forces which are opposing the flow are a function of the liquid viscosity, that is mu. So by this he has defined a number which is called as Reynolds number. This Reynolds number is the ratio of inertia forces to viscous forces. So inertia forces are function of density, diameter and velocity. So you can write Reynolds number is equals to rho Vd, whereas viscous forces are function of mu, that is viscosity of the fluid, that is mu. Now you can replace this average velocity with the mass flow rate of the fluid, and the Reynolds number will become 4 into mass flow rate of the fluid into mu pi d. These conversions we have discussed in the previous section. So this Reynolds number is mostly useful in quantitatively describing the flow characteristics of a fluid flowing either in a pipe or any surfaces of objects of different shapes. So if Reynolds number is say less than 2100, we can characterize the flow as laminar flow. If the Reynolds number is between 2100 and 4000, the flow can be signified as transitional flow. When the Reynolds number is greater than 4000, it indicates the flow is turbulent, and it also indicates the energy dissipation. When the flow is high, the energy dissipation is also high. So this type of experiment is conducted by Reynolds to understand the flow behavior. Now let us solve a problem to further understand. Say there is a 3 centimeter inside diameter pipe is being used to pump liquid food into a buffer tank, and the tank is 1.5 meter diameter and 3 meter is high. The density of the liquid is 1040 kg per meter cube and viscosity is 1600 into 10 power minus 6 Pascal second. So there is a pipe which is taking a liquid food into a tank, and they have given the diameter of the tank and the density of the liquid. So they have given two problems. First one is, what is the minimum time to fill the tank with this liquid food? It is flowing under laminar conditions in the pipe. So we have to calculate the time required to fill the tank. So let us first write down the given data, that is the pipe diameter, tank height, tank diameter, density of the liquid and viscosity of the liquid. So how we are going to solve this problem? By first determining the Reynolds number. Because we know the flow is laminar, we can consider Reynolds number as 2100. By using Reynolds number, we can determine the velocity of the fluid because the other properties are given. So here you can see by Reynolds number is 2100. So Reynolds number is rho Vd by mu. From this you can calculate V. V is 0.108 meter per second by substituting the values of the density of the fluid, diameter of the pipe and viscosity of the fluid, which is given. Now we know volumetric flow rate is nothing but area into velocity. So here the pipe is a circular pipe, pi by 4 d square is the area. So d square is 0.03 meter square into V. V is 0.108. So you can get 7.63 into 10 power minus 3 meter cube per second. So this is the volumetric flow rate. Now if you know the volumetric flow rate, from this you can calculate the time required to fill the tank. Say volume of the tank is given is 5.3 meter cube. Now you can calculate the time required to fill this 5.3 meter cube volume of tank with a flow rate of 7.63 into 10 power minus 5 meter cube per second. Simply divide this 5.3 with the flow rate, you will get, because the flow is meter cube and this is meter cube per second, you will get second, that is 6.95 into 10 power 4 second, that is 19.29 hours is required to fill the tank. So here we have used a different approach to determine the time required to fill a tank based on Reynolds number. Now we will solve the remaining part of the section. We will see the remaining question, that is second part. What will be the maximum time to fill the tank if the flow in the pipe is turbulent? Now the flow in the pipe is turbulent, then how can you proceed? So in part B you can take the Reynolds number as 4000 because the flow is turbulent. From this you can calculate the average velocity, that is, and from like in the above section you can calculate volumetric flow rate and then you can calculate the time required. So here you can see the time required is 10.16 hour and here the time required when the flow is laminar is 19.29 hour. From this you can calculate when the flow is turbulent, the time required to fill the tank is significantly reduced. So by this way we can solve various problems related to fluid flow by using Reynolds number. Thank you.